Now next topic is polynomial rings. Let R be a ring Rx is equals to a0 plus a1x so on till an x to the power n such that a0 and so on till an. This belongs to ring R and n belongs to natural number union 0. Under the operations of polynomial addition and polynomial multiplication, forms a ring called the ring of polynomial over R with indeterminate x. R is a ring. Rx is equals to a0 plus a1x so on till an x to the power n such that a0 so on till an. This belongs to ring R where n belongs to natural number union 0. Under the operations of polynomial addition and polynomial multiplication, this forms a ring and this ring is called the ring of polynomial over R. Now some properties. First, if R is a CRU, commutative ring with unity, then ring of polynomials Rx is also a CRU. If R is an integral domain, then Rx is an integral domain. Third, the units in ring of polynomials are the units of R if R is an integral domain. Fourth, if R is a commutative ring with unity, Px is equals to a0 plus a1x so on till an x to the power n, this belongs to Rx, is a unit in Rx if and only if a0 is a unit in R and a1 a2 so on till an. These are nilpotents in R. Fifth property, if I is an ideal in R, then Ix is equals to a0 plus a1x so on till an x to the power n such that a naught, a1, so on till an. This belongs to I and n belongs to natural number union 0. So if I is an ideal, then I have formed the polynomial ring for this ideal I. Then this is an ideal in Rx. Means I is an ideal in ring R and Ix is an ideal in ring of polynomials. Note, first, if I is a prime ideal in R, then Ix is a prime ideal in Rx. Second, if I is a maximal ideal in R, then Ix is never a maximal ideal in Rx because if R is a field, then this does not imply that Rx is a field. Means Rx is never a field. So that's why Ix is never a maximal ideal in ring of polynomials. Next, if I have psi a mapping from ring of polynomials to R by I, this is like quotient ring of polynomials. It will be defined as psi a0 plus a1x so on till an x to the power n. This is equal to a0 plus I plus a1 plus I x so on till an plus I x to the power n. Then psi is an onto homomorphism kernel psi. So kernel psi will be, if I call this as fx, fx belongs to Rx such that psi of fx is equals to identity of this quotient ring. Its identity will be Ix. So finally this will be Ix only. Now by first isomorphism theorem for rings, Rx by Ix R by Ix Rx by Ix is isomorphic to R by Ix. Next is the division algorithm. Let F be a field and fx comma gx belongs to fx. Gx is not equal to 0, then there exists unique qx comma rx belongs to fx such that fx is equals to gx into qx plus rx. Here either rx is 0 or degree of rx is less than degree of gx. Remainder theorem. Let f be a field A belongs to field and fx belongs to fx. Then fa, this is the remainder when fx is divided by x minus a. Next is factor theorem. Let f be a field A belongs to field, fx belongs to fx. A is a 0 of fx if and only if x minus a is a factor of fx. Means a is a root of fx if and only if x minus a is a factor of fx. Next theorem. Let R be an integral domain. Then first thing, ring of polynomials Rx is an integral domain. Second thing, the units in Rx are the units in R. Third thing, degree of fx into gx is equals to degree of fx plus degree of gx. Next definition is principal ideal domain, PID. An integral domain R is called a PID if every ideal I in R is principal. Implies for every ideal I in R, there exists an element in ring R such that this ideal I is generated by this A. So an ideal R is called a PID if every ideal I in R is principal. Next theorem. Let F be a field, then Fx is a PID, and if I is a non-zero ideal, in Fx when I was an ideal in ring R, then it was generated by this A. Now I is an ideal in Fx, ring of polynomials, whose coefficients are from field. So here ideal will be generator Gx. And this will happen if and only if Gx is a monic polynomial of minimum degree in I. Next topic is irreducibility of polynomials. Very important topic. First is irreducible polynomials. Let D be an integral domain. Fx be a non-zero non-constant polynomial in dx, then Fx is irreducible in dx over d if whenever Fx is equals to gx into hx, either gx is a unit in dx or hx is a unit in dx. So what is a irreducible polynomial? D is an integral domain. Fx is a non-zero non-constant polynomial in dx. Then Fx is irreducible whenever I can write Fx as gx into hx, where either gx is a unit in dx or hx is a unit in dx. Now some examples. First, Fx is equals to 2x squared plus 2. This belongs to qx. Now Fx can be written as 2 into x squared plus 1. Here 2 is a unit in qx. So this means that Fx is irreducible over rational. Second example, Fx is equals to 2x squared plus 2. This belongs to zx.
2 यूनिट कैसे होगा? यूनिट तो जैसे सिर्फ 1 नहीं होगी, 1 into a equal to a into 1.
यूनिट का मतलब क्या है? मल्टीप्लिकेटिव इनवर्स मिल जाए
हाँ,
तो 2 का मिल जाएगा ना. 2 का इनवर्स क्या होगा? 2 1
by 2.
1 by 2 होगा ना. 2 into 1 by 2 1.
अच्छा, ठीक.
Now in zx, fx is equals to 2 into x squared plus 1. Now here neither 2 is a unit in zx nor x squared plus 1 is a unit in zx. This means that fx is reducible over z. So this means that whenever neither this is a unit nor this is a unit, then it will be reducible. Third example, fx is equals to x square minus 2. This belongs to qx. This can be written as fx is equals to 1 into x square minus 2. Now here clearly 1 is a unit in q. So fx is irreducible over rational. Now tell me fx is equals to x square minus 2 is reducible or irreducible over Rx. Check this.
इरेड्यूसिबल ही होगा ना, इसको भी हम 1 into x square minus 2 लिख सकते हैं, तो 1 is a unit in Rx.
देखो पहले मैं ये qx वाला बताती हूँ. qx वाले में x स्क्वायर माइनस 2 को x माइनस रूट 2 एंड x प्लस रूट 2 लिख सकते हैं. ठीक है. ऐसे भी सोच सकते हो कि जो इसके रूट्स आ रहे हैं प्लस माइनस रूट 2 डज नॉट बिलोंग्स टू रैशनल. तो ये इररिड्यूसिबल है. रिड्यूस नहीं कर सकते ना, दो फैक्टर में ब्रेक नहीं कर सकते. ठीक है. नाउ हियर it will be x minus root 2 and x plus root 2. Both the roots belong to real numbers, so it is reducible. Next, fx is equals to x square plus 1. Check irreducibility over R and complex numbers. Check and tell me.
It is irreducible over R but reducible over complex numbers.
Yes. So its roots will be plus minus iota. Okay. So this is irreducible over R but reducible over complex numbers. Note, let F be a field. Fx belongs to Fx. Be a non-zero. Non-constant polynomial over F. Then F is irreducible over F if and only if, over F if Fx cannot be expressed as a product of two polynomials of lower degree. Now here also it was expressed in the form of lower degrees, so that's why it was reducible. It cannot be expressed in terms of product of two polynomials of lower degree, so it is irreducible. Next is irreducibility test. First is for degree 2 or degree 3 test over a field. So let F be a field. Fx belongs to Fx. Be a non-zero polynomial in Fx of degree 2 or degree 3, then Fx is irreducible over F if and only if Fx has no root in F. So F is a field, Fx is a non-zero polynomial in Fx of degree 2 or degree 3. Then Fx is irreducible over field F if and only if Fx has no root in field F. ये वही है जो मैं यहाँ पे बता रही थी कि रूट बिलोंग कर रहा है या नहीं कर रहा. मीन्स अगर रूट आपका बिलोंग करेगा तो रिड्यूसिबल, if root does not belong then irreducible. Examples: Fx is equals to x square plus 2x plus 2. This belongs to Z3x. Now degree of Fx is 2 and Z3 is a field. So I need to check whether Fx has any root in Z3 or not. Simply Z3 is my 0, 1, 2. I will put x as 0, it will be 2. F1, it will be 4, and modulo 3 it will be 1. F2, 4 plus 4 plus 2, 10, and modulo 3 it will be 1. So clearly none of them is equal to 0. So that's why Fx has no root in Z2. Sorry, Z3. So Fx is irreducible over Z3. Example 2. Fx is equals to x square plus 1. This belongs to Z2x. Check and tell me whether it is reducible or irreducible over Z2.
Reducible.
Yes. Degree of Fx is 2. Z2 is field. Why it is reducible?
F1 is 0. 1 is the 0 of this one.
Yes. F0 is 1. F1 is 0. So it has a root. So Fx is reducible over Z2. Next note. Let F be a field. Fx belongs to Fx. Be a non-zero polynomial in Fx. Such that Fx has a root in field F. This means that Fx is reducible over field F. So if it is reducible, then it can be written as fx is equals to x minus a into gx. Second, if f is a field, fx belongs to fx such that degree of fx is greater than 3, then fx may be reducible over field f, even though it has no root in field f. Now here f is a field, fx is a polynomial in fx such that degree of fx is greater than 3, then fx may be reducible over field f even though it has no root in field f. For example, if I take fx is equals to x to the power 4 plus 2x square plus 1, this belongs to qx. Now it can be written as x square plus 1 into x square plus 1. So this was a 4-degree polynomial. I have reduced this into a product of lower degree polynomials. Their roots are plus minus iota, which clearly does not belong to rational numbers. Then also this is reducible. This implies fx is reducible over rational, but it has no root in rational. Now second test. Reducible over rational implies reducible over integers. Now what does this mean? If fx belongs to zx is reducible over rational, then it is reducible over integers. Note, fx belongs to zx is irreducible over rational, fx is reducible over irreducible over integer only if fx is monic. So fx is reducible over rational implies fx is reducible over integers, but if fx is irreducible over rational, then if fx is monic, then we will say that fx is irreducible over integers. Next test, third, Eisenstein criteria. Let fx is equals to a0 plus a1x so on till an x to the power n. This belongs to zx if there exists a prime p such that first thing, p divides a0, p divides a1 so on till p divides an minus 1. Second thing, p does not divide the leading coefficient an, and p square does not divide a0. then we will say that fx is irreducible over rational. Example, fx is equals to 3x to the power 5 plus 15x to the power 4 minus 20x to the power 4 plus 20. This belongs to zx. Now I need to find a prime number p such that firstly it should divide the constant, means 20.
It's 20 x power 4 or 3 or 2?
क्या? Yeah, 20x to the power 4.
15 भी x power 4 है.
हाँ 15 भी यही है.
Same है दोनों.
So prime number p will be, p should divide a0 and a0 is 20. Prime number p will be 5. So p does not divide 3. P does not divide an. An is 3. P square does not divide a0. P square does not divide 20. P square will be 25 na? 25 does not divide 20. P divides a0 means P divides a0. P divides minus 20 also. P divides 20 also. P divides 15 also. 5 divides 15. So by Eisenstein criteria, fx is irreducible over rational. Next, let f be a field. A is a non-zero element from this field f if fx plus a is irreducible over field f, then fx is irreducible over field f. Example, pth cyclotomic polynomial. Let p be a prime. Phi px. This is equal to x to the power p minus 1 upon x minus 1, x to the power p minus 1, x to the power p minus 2, so on till x square plus x plus 1. This is irreducible over rational. मीन्स काफ़ी बार ऑप्शंस में जब इरिड्यूसिबिलिटी चेक करने के लिए पूछा जाएगा तो आपको ये वाली फॉर्म याद रख लेनी है कि कभी साइक्लोटॉमिक पॉलिनोमियल आ गया, p यहाँ पे प्राइम नंबर है, देन इट विल बी इरिड्यूसिबल ओवर रैशनल. नेक्स्ट टेस्ट इज mod p irreducibility test. Let fx belongs to zx. Degree of fx is greater than equal to 1 if there exists a prime p such that fx bar is irreducible over zp degree of fx bar is equals to degree of fx, then fx is irreducible over rational. Fx bar is a polynomial in ZPX obtained by reducing the coefficients of fx modulo p. Fx is a polynomial in Zx. Degree of fx is greater than equal to 1 if there exists a prime p such that fx bar, which is computed by reducing the coefficients of fx modulo p over zp, degree of fx bar and degree of fx. If they are same, then fx is irreducible over rational. For example, fx is equals to 21x cube minus 3x square plus 2x plus 9. This belongs to Zx. Now if I take prime p, prime number p as 2, then fx bar will be, can you tell me what will be fx bar?
It is x cube minus x square.
माइनस एक्स स्क्वायर नहीं, जब भी माइनस भी होगा ना तो भी उसको भी प्लस में ही लिखो, प्लस एक्स स्क्वायर.
अच्छा अच्छा ठीक है. हाँ, प्लस एक्स स्क्वायर प्लस 9
9 मॉडुलो 2 1.
हाँ ये 2 था ना, तो 0 हो गया ना, 1 9 2 4 जा 8. अच्छा 1 ठीक.
Now by degree 2 or degree 3 test over a field, fx bar has no root in Z2. You can clearly see this. Z2 is 0, 1. F0 bar, this is 1. F1 bar is 3. Modulo 2, it will be 1. So fx bar has no root in Z2. So this means that fx bar is irreducible over Z2. Also, degree of fx bar is equals to degree of fx, which implies that fx is irreducible over rationals. Next, note the converse of mod p irreducibility test need not be true. A polynomial fx belongs to Zx may be reducible for every prime p over Zp, but still be irreducible over rational. Converse of mod p irreducibility test need not be true. If I have a polynomial fx from Zx, this may be reducible for every prime p over Zp, but still it will be irreducible over rational. For example, x to the power 4 plus 1. This belongs to zx. This is reducible over zp. For every prime but it is irreducible over rational. For every prime p, if I take p equal to 2, then x to the power 4 plus 1 over z2. z2 is 0 comma 1. So if this is fx, then f0 is 1, f1 is 2, modulo 2, it will be 0. So it is reducible over z2. Next result. It's a very important result. Let f be a field Px belongs to fx be a non-zero polynomial ideal Px. This is a maximal ideal in fx. If and only if Px is irreducible over field f. For example, fx is equals to x squared plus 1. This belongs to Rx. This is irreducible over R because its roots are plus minus iota, which does not belongs to R. So as this is irreducible, so ideal x squared plus 1 is a maximal ideal in Rx. Implies, so if this ideal is a maximal ideal, then Rx by x squared plus 1, this will be a field. Now next is, before studying unique factorization domain, we will discuss some definitions. First definition is associates. Let D be an integral domain. A and B. This be non-zero elements in D. Then A and B, these are associates if they differ by a unit. This means that there exists U non-zero belongs to D. This is a unit in D such that A is equals to UB. D is an integral domain. A and B are non-zero elements in this integral domain D. Then A and B are said to be associates if they differ by a unit. There exists a non-zero unit in this integral domain D such that A is equals to UB. For example, 2 and minus 2. These are associates in Z because units of Z are 1 and minus 1. So if A is 2, B is minus 2, then 2 is equals to unit into minus 2. So minus 1 can be put here because this is a unit in integers. Next, 2 and 4 are associates in Z5. So A is 2, B is 4, 2 is equals to dash into 4. Tell me what will be the unit here?
3.
Yes. Let A and B belongs to integral domain D be associates. Then generator A is equals to generator B. Next is irreducibles. Let D be an integral domain. A non-zero element belong to integral domain D be a non-unit. Then A is irreducibles in D if whenever B comma C belongs to integral domain D such that A is equals to BC implies either B is a unit in D or C is a unit in D. D is an integral domain, A is a non-zero element from this integral domain D. This is a non-unit. Then A is irreducible if whenever B and C belongs to integral domain D such that A is equals to BC, where either B is a unit in D or C is a unit in D. Next is primes. Let D be an integral domain. A, which is non-zero, belongs to D, is a prime. If A is not a unit in D, and whenever A divides BC, then either A divides B or A divides C. Next note, in an integral domain, prime implies irreducible. Second, let D be an integral domain. A belongs to D. This is a prime in D if and only if generator A is a prime ideal in D. Next, norm. Let D be a square free integer. Z root D. This is equal to A plus B root D such that A and B are integers. Now define a function Z root D to set of integers, set of positive integers union 0 as norm A plus iota B is equals to mod of A square minus B square D. Now it has 4 properties. Those 4 properties are, first thing, norm of x is equals to 0 if and only if x is equals to 0. Second thing, norm of xy is equals to norm of x into norm of y. Third property, norm of x is equals to 1 if and only if x is a unit. Fourth thing, if norm of x is prime, then x is irreducible in Z root D. Some remarks. In an integral domain, irreducible need not be prime. Means converse of this first point need not be true. For example, in Z under root minus 3, 1 plus root minus 3. This is an irreducible but not a prime. एक सेकेंड रुकना है, कॉल आ रहा है. स्क्रीन विजिबल है ना?
Yes, ma'am.
So this is an irreducible but not prime. Next is PID. An integral domain is a PID if every ideal is a principal ideal. For example, integers is a PID. Second thing, every field is a PID. Third thing, if F is a field, then Fx is a PID. Converse is also true. Fourth, Zx is not a PID. Generator 2, x. This is not a principal ideal. In sets. Next note, in a principal ideal domain, irreducible if and only if prime. Second, in a principal ideal domain, every non-zero prime ideal is maximal. Third, the quotient of a PID by a prime ideal is a principal ideal domain. Now next is UFD, unique factorization domain. Unique factorization domain, UFD. An integral domain is a UFD if first every non-zero element in D that is not a unit in D can be written as a product of irreducibles in D and second thing, the factorization is unique up to the associates except for the order in which the factors occur. Example, every PID is a UFD. Second, Zx is a UFD. So what is a UFD? An integral domain is a UFD if every non-zero element in D that is not a unit can be written as a product of irreducibles in D, and this factorization is also unique up to associates except for the orders in which the factors occur. Next is Gauss theorem. Let R be an integral domain. R is a UFD if and only if Rx is a UFD. Note Z root minus 3. This is not a unique factorization domain, as 4 is equals to 2 into 2. This can be written as 1 minus under root minus 3 into 1 plus under root minus 3. This is two different factorization of 4 in Z root minus 3. This is irreducible, which are not associates. For d less than 0, Z root d. This is a UFD only when d is equals to minus 1 or d is equals to minus 2 only. Next is Euclidean domain. An integral domain D is a Euclidean domain if there is a function called norm D mapping from d minus 0 to z plus union 0 such that it satisfies the following properties. First property, dA is less than equal to dAB. Second property, if A comma B belongs to D, B is non-zero, then there exists Q comma R belongs to D such that A is equals to BQ plus R, where R is 0 or dr is less than dB. For example, every field is an Euclidean domain. Second example, Z is an Euclidean domain. Norm can be defined as D mapping from Z minus 0 to Z plus union 0 as dA equal to mod A for all A belongs to Z. Third example, let F be a field D is a mapping from Fx polynomial ring minus 0. It will be mapped to Z plus union 0 as df is as degree of fx. dfx is equals to degree of fx. Fourth, Z iota, ring of Gaussian integers, is also an Euclidean domain. It can be defined as Z iota minus 0, which which is mapped to z plus union 0 as dA plus iota b is equals to a square plus b square. ठीक है. Next theorem. Let f be an integral domain, then the following are equivalent. First thing, f is a field. Second thing, f is an Euclidean domain. And third thing, f is a PID. Now some remarks. Subring of an integral domain is an integral domain. These remarks are important. Second thing, subring of a unique factorization domain need not be a UFD. For example, C is a UFD, Z root minus 3 is a subring of C, but not a UFD, which is not a UFD. Third, subring of a PID need not be a PID. For example, QX is a PID. ZX is a subring of QX. Which is not a PID. Fourth, subring of a Euclidean domain need not be an Euclidean domain. For example, C is a Euclidean domain. Z theta, this is a subring of C, which is not a Euclidean domain. Here theta is equals to 1 plus under root minus 19 by 2. Fifth, the irreducibles of Z iota, these are, first thing, 1 plus iota. Second, P belongs to integers, a prime of the form P congruent to 3 mod 4. Third, if P belongs to integers, is a prime of the form P congruent to 1 mod 4 implies P square is equals to A square plus B square, then A plus iota B, A minus iota B, B plus iota A, B minus iota A. These are irreducibles. Sixth, if R is a commutative ring with unity. Sixth is basically conclusion. If R is a CRU, then Rx is a CRU. R is an integral domain, then Rx is an integral domain. If R is a UFD, implies Rx is a UFD. If R is a PID or an Euclidean domain, then this does not imply that Rx is also a PID or Euclidean domain. For example, Z is a PID, but Zx is not a PID. Conclusion. Every field is an Euclidean domain. Every Euclidean domain is a PID. Every PID is a UFD. And last, every UFD is an integral domain. Means field implies Euclidean domain implies PID, PID implies UFD, and UFD implies integral domain. So I can use its negation also. Not integral domain implies not UFD. Not UFD implies not PID. Not PID implies not Euclidean domain. Not Euclidean domain implies not field. Because we know that every field is an integral domain and not an integral domain implies not a field. Note, first, integral domain does not implies UFD. For example, Z root minus 3. This is an integral domain but not a UFD. Second, UFD does not imply PID. Example is Zx is a UFD but not a PID. Third, PID does not imply Euclidean domain. For example, Z theta. This is a PID but not a Euclidean domain. Where this theta is equals to 1 plus under root minus 19 by 2. Fourth, Euclidean domain does not imply field. We know that Z is an Euclidean domain but Z is not a field. So this means that field is contained in Euclidean domain is contained in PID is contained in UFD and UFD is contained in इंटीग्रल डोमेन. ठीक है, तो थ्योरी पोर्शन यहाँ सारा हमारा कंप्लीट हो गया. अब जो आज टॉपिक हमने पढ़ा है उससे रिलेटेड क्वेश्चन कल हम प्रैक्टिस करके रिंग थ्योरी कंप्लीट कर देंगे.
ठीक है.